So despite the longer videos this time, we're already well over the usual total amount of video time I give you for a day. So we'll wrap this up quite quickly. And we'll just think of this as kind of we'll put a pin in this and then come back to it next time. But I wanted to give you pseudocode for an implementation of what I just showed. And so what this code does is it takes in an array containing the denominations that we're interested in. So D here is an array of denominations, and then N is a change amount. And what we do is we first initialize this C array. So this C array is essentially catching the N that we showed earlier. In fact, we might as well just replace all of our C's with capital N's, because that'll make it clearer in terms of the walkthrough that I gave in the previous video. Okay. All right, so what we do is first we say n of 0 is 0, right? N is going to represent our DP table that stores the optimal change amounts. So this isn't storing the optimal change. The algorithm would need a little bit more in it to store the actual change, the actual denominations that come into play here. It wouldn't need very much, right? You just need one extra kind of row or column in this table. But you can think of this n as our DP table. It's storing the amounts of coins that are needed for each denomination. It's clear that it takes 0 coins to do 0, so we just initialize n of 0 with 0. And that represents the number of the number of coins to make change for 0. Or I'll just say make 0. Okay? So there we go. And that'll be true for any problem. And so then we set up a for loop that looks at every single one of our change amounts, and so we'll just iterate through those. For each change amount, we're going to try to find a minimum of several numbers. So one of the ways of finding a minimum is you initialize something large, and then you start comparing that to the thing you've seen so far, to all the things you've seen so far. And as you go through, you compare where you are to the smallest thing you've seen so far, and then where you are right now is smaller, you stick that in the smallest thing you've seen. So here we go. The smallest thing we've seen so far at first is infinity, right? So that's saying we haven't seen anything yet. And so then we'll set up this is implemented as a while loop. I believe this code is almost directly from the textbook, the code, that version that's in my notes. So this isn't, the cleanest way to do it necessarily, but we'll set up a while loop that starts at 1, and it says, go through each denomination. We'll iterate through the denominations like this, and we'll only look at denominations that are smaller than the change amount we're trying to make. So like when we were trying to make change for 2, we just ignored the fact that we had coins for 3 and 4 because they're too big, right? They don't make any sense to consider for making change for 2. So that's what this little check here is doing, is it's checking to see if the coin could even possibly make sense for this amount. And so then we're iterating through the denominations, and for each denomination we say, hey, how many coins, if this coin, this denomination is part of our optimal change, how many coins would that leave left? And then we go look up in our table and find out. And then if that's smaller than the smallest thing we've seen so far, we store it in our temp. We increment j and then continue. Right? So this while loop is really a for loop with some extra logic embedded in it, some extra breaking logic. So once we're done, then we say, okay, once this while loop is finished, we have now identified the optimal number of coins to make change for this. And so we now store that in our DP table. And the +1 is that +1 that I had for every single one of my other ones that says there's going to be a coin, right? So it's a coin plus optimal change for some other set of coins. So there we go. And then we do this for loop, and when the for loop terminates, we just return the thing at the end, right? Because by construction, we've made this thing give us the optimal change for each change amount, including the last one. So what's the time complexity? Well, I hope it's clear that we have a for loop that has n iterations, and then we have a while loop that has m iterations, right? Our while loop on almost all of these is going to have exactly m iterations, all but the first couple. And so the complexity is n times m, right? So complexity n times m, so big theta of n times m. And this is in a worst case scenario where we do all of the iterations. Now, what happens if we have a best case scenario, right? Is there a best case scenario? Well, here a best case scenario might be something like we don't have any denominations. We don't have any denominations that can make change. And so this is something we can think about going forward. And we'll look at more examples of this problem, I believe, on the homework, and then also in the next set of lectures. But overall, we have essentially two fixed length for loops. So our best case complexity is n times m. So that'll wrap it up for now, and we'll have more coin change fun and some knapsack stuff coming up next.